Good morning and welcome back to the Vegas October 1 Sounds channel. Today is going to be a little bit fun because I'm not going to talk about the deep-seated theory of God's existence as I tend to get into with the math behind some of this stuff. I'm just going to show you some of the tools that I use to ask questions. Now, at heart, I'm a tinkerer. I love to look at things, tear them apart, see what makes them work, put them back together, and then understand how they work, basically. But as an engineer, I have to make things work. I got to know that when I step on the brakes in my car, that computer in there, which is controlling the anti-braking system, isn't going to fail because somebody's life's at stake. So for me, I collect information, I create models, I put the models into real products, and those real products got to work. I don't have the luxury of speculating that, well, yeah, you know, it's probably going to stop the car. Geez. Anyway, so most of the time what I'm doing is asking questions, and I am a lifelong learner. In fact, there's so many outstanding questions that I have in my life that sometimes it's kind of mind-boggling. One that I contemplated last year was, where does gold come from? And people say, well, it's easy, it comes out of the earth. I said, well, of course it does, but how to get there? Well, this planet was formed by aggregation. I say, okay, that's great. So you mean that somewhere along the line there was a bunch of gold floating through the cosmos, and due to some phenomena like gravity, maybe it got just all collected here, right? Yeah, that's right. I say, okay, great. Well, how did it get floating in the ether out there? And people would say, well, it was made by a star. I said, okay, you mean like ours? And then they'll say, well, not really. Oh, you're damn right, not really, because our star generally only can produce, the heaviest element it'll produce is iron before it vaporizes itself out of existence or just dies a cold death. And so then they start telling me how the fusion process that goes on in the inside of the stars, where you're combining lighter elements into heavier elements, and eventually that combines these elements into iron. That happened somewhere in a star that was much more massive than ours, and then it blew apart, and it spewed its guts all over the universe, and the guts contained gold. I said, okay, well, what kind of star was that? And they said, well, the only star that would be energetic enough, because it takes energy to fuse these particles together, would be a supernova. And I said, a supernova? I haven't seen one of those recently, and damn well better not, because when those things go, they literally fry things for light years. A supernova explosion, even 4 light years away from this planet, if any of the rays were directed this way, would essentially eradicate all life on Earth. And I go, so now all the gold in this planet came from a supernova at some time, which blew its guts across the universe light years apart, and those all came back together and gave us gold on this Earth. And they said, yeah, that's right. I said, well, that's a hell of a theory. So then I start looking go back to the fusion process inside stars, start looking at the mass of the stars, and when gold can be produced and all that. And come to find out, even our sun has gold inside it. Not because it has produced it, but because somewhere, sometime, some other star produced it. It snuck into our star, into the sun, and now because it's there, it's actually adding to it just a little bit. And the first time I approached an astrophysicist, or a proclaimed expert in the field, let's just say, with that concept, he said, "Oh, that's a crock of shit." He says, "No, our sun's not heavy enough to support that type of a fusion process." I said, "You're right. Generally, it's not. But the sun isn't a linear system. It's a nonlinear, chaotic, dynamical system that has all these little pockets in it that can. There's little pockets in the sun that are denser than other parts. It happens. Just like there's whirlpools in streams, or patterns on the beach caused by the waves. These things happen. They emerge." And so you quickly learn that never to accept the standard theory until you have a deep understanding and you can question everything. So I question everything. Today I'm going to present a couple of the things that I do to question everything that leaves me with a bunch of nagging questions, but maybe the information will be useful to somebody. So if I take my standard set of videos here, and that's nothing more than what this is basically a time graph of all the volleys for about 21 videos. Why 21? Well, that's a subset of what I have, but you start putting in all your videos and it gets out of hand quickly. So for example, over here on the first shots, I have no less than 20 videos that I have used to take a look at the first shots, but if I put them in there, it'd just be one big black mess. So I stick with this base 21, and when I want to work outside of it, I create a new scenario, a new chart, and go with that. What this chart does is show you in a fixed time frame. It places events in a fixed time frame on a fixed scale so that you can see the relationship amongst them. So for example, over here we have the tail end, and we're at about 600 seconds. I put this in seconds with a little printout every minute for a really good reason, and that is that this whole damn thing seems to be pretty regular, and that bothers me. For example, these gaps between the volleys, that's pretty close to being the same. It's pretty close to being the same over here, and then you do a bunch of crap where you're doing nothing apparently, and you come back over here. And this regularity, these patterns, these maybe an emergent phenomena, that bothers me. That makes me ask questions. So I put all these volleys there. There's no real great detail from each volley, but you get the idea that there might be something more to this picture than looking at the individual shots. So the graph starts right here. I start with the first available minute where the first major volley starts, which is 10:05 for this column, and that's why these numbers are negative. So this would be 10:06, 7, 8, on out to the end of the volleys as I know them. And then what we do is we take the absolute time that the volley starts from the perspective of one point in the entire venue. We all know that when the shots happen, it takes time to propagate the sound outwards. And for every different recording position, there's a slight delay in when you hear the sound. This graph eliminates that head delay, such that volley 1 for this purple one, what's a purple one? That's the Hartman video. And here on the orange one, which is, I think that's metal, and then the lighter orange, which I think that's something else. Anyway, all start at the same time. And if we zoom in on this, you can see that, yeah, they're perfectly aligned, because that's probably because I started them all at the exact same time. So this gives me an idea of what's happening. And the alignment process is something that I'll get into. And then I wrote a little program to scrunch them all together in a way that looks good. You can't just lay them out willy-nilly, because you lose some value there in terms of what you're seeing. For example, you can see a little detail here. If we jump over to 6A, you'll see that even though I've aligned things, there's some discrepancy here, which means that there may be some differences in the time between volleys, or maybe I screwed up, or maybe the phone recording that video was moving, or maybe the shooter was moving. But the fact that you can even do this says a whole lot about the scenario. If there were multiple shooters, this graph would not be possible, because multiple locations means different timing from the shooter's perspective. So for example, if there were two shooters, let's say, and one was responsible for half the volleys, when we tried to line them up, all of the shooter ones would line up perfectly, but then all of shooters 2 would line up in a different fashion, and they would not be nice and neat. The shooter 2 would be skewed all over the place, unless there were very special circumstances and locations that the shooters were in. A better example would be, let's say that all these sounds really were coming from the speakers on the stage. And okay, that's a possibility, and not very likely. In fact, it's absolutely not possible for my data. Then this graph would end up being, if we lined up if we took a sound from the speaker, let's say like one of the songs, and we lined up all the videos with that song, because after all, the sound is coming from it, then these would have to line up too, because they'd have to be coming from the same source. But when I do that, they don't, therefore they're not coming from the speakers. So it's a powerful technique, which I think that's more than I want to say at the moment about that process. So anyway, this is a global picture. We're focusing on global big picture issues today. And as you can see, this is a work in progress, always is, because these should be the same size and start at the same place, and they don't. This one over here is short, meaning I haven't finished it. It's got a little piece there, so obviously I'm still working on that. There's something down there that needs to be addressed. Let's see. I had to have to look closer, so I can come to this actually and see where I'm working at. There's misalignment there or something. And it's interesting that the 6A shots here, there's two different types of alignment. That one right there is a little wider. All these little details that over time you look at and you figure out what's going on, and you either correct, or you build a model and a database of what's going on. So let's see. Let's start asking questions. All right. Presuming for the moment that there was one person doing the shooting, then he'd have to be responsible for all the timings here. That's good. So let's look at this. Alright, well, we got a big gap here. This is divided into 5-second increments. So if we come over here and we look at this volley, then we see we got a part of, let's magnify it more. We got 5, 10, 13, probably about 14 and a half, 15 seconds between these things here. Okay, 15 seconds. If we come over here or look, 1, 2, 15, 18 or 19. Here we have 1, 2, 3, 4. That's 20. Here we go. 1, 2, 3, 4, 5, 6, 7. That'd be 35 plus some. Similarly over there, blah 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 blah. So remember, we got the hypothesis. It's one guy. So if we look at the gaps and we say what's the minimum gap that occurs between volleys, it's probably on the order of 15 seconds. 15 seconds. 15 seconds. Oh, 20. 15 seconds. 15 seconds. You get the idea? All of a sudden, how the hell did you consistently get 15 seconds between happenings when you're up there like a madman shooting like a motherfucker killing people, and yet you got the cool, calm, and collected ability to maintain this? I got questions about that. Okay? But yet it is what it is. But furthermore, you can also look at this and say, when did he have time to do what? So, based upon this graph alone, you would say that something was happening here that didn't result in volleys but took time. Similarly there, maybe there. Certainly here. And this timing is interesting too, because somebody claimed that there were shots down the hall at Campos early on, and the only place they're possible is right here or there. And given the testimony of other witnesses, you soon determine that right there is where they had to occur, and if you can demonstrate that they didn't occur there, then the whole thing blows apart from the testimony standpoint. Similarly, you can ask, or hypothesize anyway, that, okay, here I am, I'm shooting along like a crazy motherfucker. Pardon my language, but this just bothers me sometimes. What am I doing? What determines these minimum times? And theoretically, you had to run from room to room sometimes. Let's see, the 8 shots in the middle were in a different room, right? Or, excuse me, over here. These are the 8 shots. And yet, from the end of the last one to this one, he only had 1, 2, 3. So a little over 15 seconds to do it. Pretty short. Pretty short indeed. Excuse me, let's see, I'm wrong on that. It was 20 seconds. These are the 6 booms, which are not done by him. That's just a marker. So he had 20 seconds. Okay. Over here we have hallway shots right here. So last hallway shot, 1, 2, 3, 15, 18 seconds later, he's dropped his gun for the hallway, cool, calm, and collected, and walked over while he's still wondering about the guy down the hall, grabbed another gun, and off to the market. So, using this graph, someone can take this and say, yeah, okay, we can time, whatever's going on between these volleys in this scenario, you can time it and then start applying it all over, because people tend to repeat the processes the same way every time, or at least you can limit it to that thinking. And then you can say, oops, something happened here. He had a heart attack, or he had to look at those monitors, or he took a leak, or whatever. And similarly here, there's reasons for all these larger caps. And that's what an investigation can look at, obviously. And people have. But perhaps this will pinpoint a few of the key elements in a graphical way. I've got all this information listed in a worksheet, but for the life of me, I can't put my mind around it. And when I put it on this chart in colors, it grabs me. And that's why I have this. Another big picture, this is just, marking out in time where these volleys occur. Another big, but a similar graph. This time what we've got is, the numbers are different, but it's the same thing. At 10:05, it's 0, and then it moves out by 100 seconds. See, I need to modify this so it's by the minute, but anyway, it still covers all the way out to the end of the major volleys. And this is a graph of RPM for, oh golly, I can't readily tell here, but probably, let's see, 1, 2, 3, 4, 5, 6, 7, 9, 10. Looks like about 12 videos. Because after all, after a few, it just starts to get collected. But this is, we measure the time between each shot for these volleys, and then calculate the rounds per minute, and plot them in an absolute scale. And now we get a picture of what was happening with the volleys over the course of time. And we can correlate that back to the other graph and say, okay, well, here's where the single shots were fired from the 308, and just prior to that he was, bumping these things off like that, and after it he was bumping them off like that, which might make a little sense because these shots, which were the volley, what we call volley 5, except for the first shot of the first volley, were all very narrowly contained within a small RPM range. So in this case you could hypothesize that there was a calming effect to these single shots, and that gave him the ability to control the gun better. Maybe. Okay, but you can ask those types of questions from this, and you can kind of spot, or you can ask, let's back up a little, you can ask this question: why does each volley vary? Okay? Why does each volley vary? And we all know volley 10 by listening is got a rather unique pattern. And you can say, well, let's go look at the pattern on volley 10. Alright, so I pull up my trusty dusty little search puppy, and I know that somewhere out there on the hard drive I've got volley 10 pieces stored. Okay, and I want to look at a time plot for volley 10. There we go. So we've got a volley 10 for Oasis. Let's take a look. Alright. So here is a graph where I just simply, for volley 10 from the Oasis apartments, I put a mark for every little delta. And so this gives you an interesting perspective on what you're hearing. We know that we're changing intervals, and with this you can see the gap between them. You can see where the intervals get larger and where they get closer together, just like a slinky, compression effect. That's one way of looking at it. But there's another way of looking at it. Let's see, there should be a stem plot in here somewhere. Show me the stem. Alright, let's do through this. A lot of data to work through. Search is essential. No stem. Sure, there must be. Oh, I see what I did wrong. I want a stem for 10. There we go. There we go. It's a stem. Alright. It's a stem plot because it's pointing lines down. So here we take that same information from the Oasis for volley 10, display it in a line graph form, and smack down a line through the middle, and we can see that we have a very interesting pattern. We can also see that there's structure to it, that it does vary, and immediately, as if all my engineering kicks in and said, oh, there's some simple oscillators going on here, that there's one and possibly two main forces driving a series of events that is oscillating around. And then my engineering mind kicks in and says, I could use that, because if this holds true for all volleys, even though the oscillations may be smaller, then I can take those two forces and say, why did the forces change? So for example, in this case, there's probably going to be, if you're using that bump stock, he has to force the handle, he has to force the muzzle away from him. That's one force, which is a spring, essentially, where the arm is the spring. And then when the trigger, when it pushes it far enough out that the trigger fires, then the muzzle is pushed back by the forces of the gas, and the internal mechanisms kick in, and the timing starts. So there's at least two there, and that's what this graph shows. And then if we were to pull up another one, it would have a different rate. So this graph confirms that the mechanism driving one part of the oscillation rate was variable. Otherwise, it'd be relatively straight line, or the gaps up and down would all be the same. So when you start looking at the detail like that versus the big picture, you can tell a lot. But you can start asking different questions. But then you have to tie that in with, we go back over to the big picture here. So that's 10. But you see, 10 is kind of dense in the middle, which means, I don't know what it means. But anyway, some of them are way big, some of them way small. But if we compare 10 to 2, for example, which I've done somewhere, you can start making some inferences that can lead you to answering some of the bigger questions that we would have here. Alrighty. Just collecting my thoughts here for a minute. You'll get used to these mnemonics over time. They're not too hard. No. I think that's it for the big question pictures, or big picture questions, really. I'm sure that some people will have different ones, and in that process, you can say, well, what if we looked at this differently? And you can always ask what if, and what ifs are really good questions. Let's see what else I did there with. I ran a scenario called catalog. Okay, so we ran a series called scenario called catalog. That's good. So I got all the graphs for that scenario, and we have events versus time. Yeah, that one we know about. Let's look at, okay, here's one. So here we have a delta history oasis 10. Let's see if that's useful. Okay, so we take that same, so here we have a delta histogram, which basically, puts the time between shots into groups, and it tells us what, it's an indicator of the variance between the shots in a group fashion. So in this case, we see that we've got 75 milliseconds here, or 0.05 seconds, has a pretty high frequency compared to the rest of these. So that would indicate that the gun has whatever mechanisms that make it prefer that timing. And you can see that this is a different group with, right about 1.1, let's say 105 milliseconds, and then it tapers off. And if you know anything about statistics, this would tell you a whole lot about the process. Alrighty. If we look at what the hell is that? Oh, okay. And this is a different style of a graph that I do use a lot. And in this case, we're plotting this across a fairly fixed scale. and we're just taking the time between the shots and then connecting a line. And this is a different way of looking at the things that happen. And this one is for Hebrew, which is taken, I know that it's taken in the Luxor parking lot by ladies speaking what I believe to be Hebrew. And it's for Volley 9C, which would be the third burst of Volley 9. Okay, and in this one you can see that if we were to draw a line right along this, then the deviations up and down are pretty regular. And they're what I would expect, actually, because if one shot is short, then by definition the next one, or excuse me, if one shot's long, then by definition the next one's going to be short. But up here we see that that little process was changed somewhat. Okay, now, can a machine gun do that? That's a good question. Let's go take a look at what the utility of this is, that you could take a look at this and compare it to any other type of gun you want. I believe that I have. Let's see. So we're delta RPM aligned. Delta RPM, and let's work it on a M240. Yeah, I don't have any. Oh, what do I have on the 240? I have a bunch, but I probably cleaned them up recently. Delta. Okay. M240B. Okay. Histo. Oh, well, as you can see, they don't look like that, but that was not a very good one. Okay. This is interesting. It's a little bit skewed. All this really says is that there's probably 3 volleys because in this case the time between the volleys was so big that it dwarfs the variations down there. Stay away from the histograms, Richard. Oh, there we go. Alright, so here's an example of the same type of graph we were looking at for Volley 10 from, or Volley 9 rather. And in this one we got 8 shots. And the variance in them ranged from a low of 107.5 to 115. Okay, so this one had from 75 to 115. So let's see, it had, my math brain is not cooked today. 25 to 1, 25, 30, 40. There we go, 40. Yeah, I'm sure most of you could calculate that quicker than me today. So this one had 4.0 milliseconds variation between the lowest and the high. Now it still looks kind of big, but we have to take the absolute value. We'd have to put it on the same scale as the other one to compare it. So let's go back over to, here we go, this, and ask the same question. This one was a high of about 7, about 8. This is RPM, so we'd have to take the inverse of it. 800, so we varied from 800 RPM down to about 560, or a difference of 300 RPM. So if we popped up our trusty dusty calculator and said 300 RPM, that would be about that much. 5e to the minus 5, which would be, let's see, Bentley 1, 2, 3, 4, 5. That's going to be about 0.05 milliseconds. So in this, I'm wrong about that. It's the other way around. Anyway, bottom line is run the numbers and you'll see that this variance here is much, much larger than the machine gun. And I have some graphs somewhere. Next time I bring this issue up, I'll be better prepared. So anyway, big picture. There's another big picture graph, the one you're going to see hundreds of times. This is a big picture graph because it gives me an overview of the whole area in a qualitative way that we can start asking questions about. This is the lag graph that shows the lag as measured from various places across the venue, mapped versus the longitude and latitude. If you're unfamiliar with this, go back to the very first video I did and it will explain it all. How does this tie into the other graphs? Well, if you're working on Volley 9 and you're out here at Oasis, then you're looking at this color here. You're looking at anywhere from 0 to 5 milliseconds. That doesn't make any sense. 5, a very small lag. And then you can pop that back over to the Volley itself and start asking more questions. Yeah. Anyway, that's it for this one for today. Have a good day and see you in the next video.